เขาบอกให้ลองเข้าไปถามเธอลองถามเธอก็กลัวว่าเธอจะจากฉันไปทิ้งเอาไว้ยิ่งไม่ดีเพราะความรักมันยิ่งล้นขึ้นทุกทีเป็นยังไงเป็นกันจะกับฉันจะลงเอยกันยังไง
เพื่อนคนหนึ่งเขาแอบชอบเธอต้องบอกเธอว่าไง
ก็แค่เข้ามาบอกก็แบบที่เธอเพิ่งพูดไป
ยิ่งเราใกล้ชิดฉันยิ่งต้องคิดว่ามีสิทธิ์ชอบเธอไหม
เธอรักมากเท่าไรฉันรักมากกว่านั้น
เปิดหัวใจวัดกันคุยกันนะมองเลย
คิดอยากไปไหมเธอก็ถามมาจะรีบตอบว่า yes sir ฉันรอจะเปิดอยู่เหมือนเธอไอ้ที่เธอคิดฉันเองก็คิดฉันฟุ้งซ่าน
ใครอธิกัดใครอวกาศเขาเรียกว่าแอบรักอะป่ะอยากให้คุยนักอยากให้พูดนักเอาเลยมาวัดกันนะป่ะเอาให้ชัดจะรักหรือไม่รักเปิดคุยเป็นล่ะเข้ามาดิครับจะทำให้รักมันชัด
อีกบางทีที่เธอทำไม่มีใจเรื่องจริงไหมหรือว่าฉันคิดไปเองลองถามใครเขาบอกให้ลองเข้าไปถามเธอลองถามเธอก็กลัวว่าเธอจะจากฉันไป
ทิ้งเอาไว้ยิ่งไม่ดีเพราะความรักมันยิ่งล้นขึ้นทุกที
เป็นยังไงเป็นการเป็นกับฉันจะต้องเอ่ยกันยังไงเปิดมาเพื่อนคนหนึ่งเขาแอบชอบเธอต้องบอกเธอว่าไง
ก็แค่เขามาบอกก็แบบที่เธอเพิ่งพูดไป
ยิ่งเราใกล้ชิดฉันยิ่งต้องคิดว่ามีสิทธิ์ชอบเธอไหม
เธอรักมาเท่าไรฉันรักมากกว่านั้น
เปิดหัวใจวัดกันคุยกันนะลองเลยคนหนึ่งเขาแอบชอบเธอต้องบอกเธอว่าไง
ก็แค่เขามาบอกก็แบบที่เธอเพิ่งพูดไป
ยิ่งเราใกล้ชิดฉันยิ่งต้องคิดว่ามีสิทธิ์ชอบเธอไหม
เธอรักมาเท่าไรฉันรักมากกว่านั้น
เปิดหัวใจวัดกันคุยกันนะลองเลย เปิดหัวใจวัดกันคุยกันนะลองเลย
คิดอะไรไว้แต่มันก็ไม่เคยกดส่งชอบเธอแค่ไหน yeah ก็ไม่เคยที่จะพูดตรงๆอยากพิมพ์เท่าไรก็ต้องห้ามใจได้แต่ทำนี้ไปยิ่งเคยแค่ขอบคุณนะ yeah แต่มือมันก็เต้นก็เพียงว่าชอบคุณนะได้แต่ลุ้นให้มันส่งไม่ติด
All good? Got a bonus? Hello. Okay, you are all in Terrace A and B, and this is for a tutorial session. If you're looking for the peering forum, you are in the wrong room. If you're looking for APNICS IPv6 deployment, you're in the wrong room. Next up, we have Dhruv from Huawei doing a tutorial session on the comparison of SDN's Southbound interface, most, I guess, popular protocols. So, Dhruv, take it away. Thank you.
Yeah. Thank you. Let me just share the screen. Are we all set? Okay. Hi everyone, I'm Dhruv. As mentioned, I work for Huawei. I've been with them for 21 years. I'm also quite active at ITF, and where I chair a PCE, which does the PCEP working group, which is one of the southbound interface that we will be talking about. I'm quite active in the traffic engineering space, segment routing, MPLS, VPNs, usual routing area. Apart from that, I'm also on the Internet Architecture Board, which looks at Internet architecture health at a very high level, how ITF is interacting with other standards bodies, other organizations like ICANN, like RIRs. So the whole I-star governance model as well. So that's another role that I play. But today, our focus is on SDN, is on the southbound interface, various protocols that exist out there. So let's get into it. Let's start with defining SDN. When SDN, we all heard the buzzword when it came out, and we all thought that's going to change the world. That's what promised to us. The idea that you could have a physical separation of network control plane and forwarding plane, where your forwarding plane can just be dumb, just put the flows there, and then control plane sits in a controller and it's going to control everything. You will have dumb device everywhere and an intelligent controller somewhere in the middle. But that's not something that actually happened. What happened is we still had SDN, but it's not a clean-cut separation of control plane and forwarding plane. Just strip your routers of the whole control plane and just put the forwarding there, and that's going to work. That never happened. What indirectly happened is more of an approach that we could have a mechanism where our networks are more programmable. Our networks run in a much easier way where we could centrally manage them. We are agile. Agile in the sense when the network requirements change, how quickly can we react to them? Does it take us 2 days to process it? Email chain forwarding, approvals from committees and boards, or can we react to what's happening in our network immediately? Add that agility, add the ability to program our networks, which are different from configuring your network. We all understand using CLI, using mechanism where you go and do configurations, but programmability is more different than that, where I can execute instructions on a particular device, which is beyond high-level configuration of configuring your IP addresses or configuring your VPN or configuring BGP, but modifying how BGP or interface is reacting to the network events. That's where the agility comes in. The idea of using open standards and being vendor neutral. So still having an interface between controllers and network device, but again, in a completely open standard, vendor neutral way. So this will be the figure at high level. We have our network devices. You have an SDN controller. The controller uses southbound interface to go and talk to these devices. And then you have something called northbound interface over the SDN controller, thinking that you can now develop innovative applications that only talks to the controller and at a high level provides its intent or its requirement of what the network services that I want in this network. You can go break them down into individual devices and then go and configure them or program them on the network device. So this is the overall ecosystem of an SDN network looks like. And you will note that the arrows are bidirectional. That means information is flowing from devices to the controller, as well as from controller to device, and the same is between in the northbound interface space. So what were the trends? What was happening in our industry which gave rise to SDN? SDN started off as a research item. It developed in a university space. The initial protocol came from there, but then industry took over, and there were a lot of trends that were changing at that time. We all saw changing traffic patterns because of cloud, because of 4G and 5G, more mobile network, the big data was rising. And the whole need that our networks needs to be more agile. While applications and cloud could have easy APIs to do modification everywhere, the networks were static. You go and you configure the network, and then there is a CLI that only a network administrator has access to. You don't react to network. And this was true for all types of network, including things that we are doing in private networks inside our enterprises, as well as what we do in public networks like ISP. Networking exists everywhere, the configurations exist everywhere. But in all of these spaces, we need this agility, which was sort of missing. And then in some cases, there was also a vendor lock-in. There were a lot of things, a lot of services which were easily provided by one vendor. And once you have bought them, you are kind of tightly knit to that vendor. It was very common in, for instance, the optical space, where you bought a device, you have to buy an OSS from the same company because, okay, nobody else is easily able to manage that. And that's where we thought that, like, the SDN world should be able to change those things. And then when we are setting up our routing and setting up paths, is the information that we look at, whether it is a network-wide optimization or just an optimization on a device. Having a controller in your network which has a global view of things, you are able to do some decisions that you were not able to do when you were only relying on what is there inside OSPF, or only relying on the routing policies that exist on the device, rather than looking at the network-wide what's happening. And then network automation, we all saw a growth of that from moving from just shell scripting to actual APIs. Things like network telemetry came into place. Idea of continuously learning what's happening in my network and making decision based on that. Intent-based networking. Again, not talking in terms of CLI, but let me just tell what I want rather than how I want it. And that's where the intent comes in. And in IETF and other places, there are initial work being done in this intent-based networking as well. So these were just very high-level trends there are. Before I continue, just one comment which I should have said at the start. If you have any questions, please raise your hand at any time. We have a microphone that can go and move around. We have 90 minutes. I don't want to be talking all the time, so it will always be good to, if you folks can interject when you have things to say, things to clarify, things to ask. Let's make it an interactive session. Are there any questions before I move ahead? Any burning questions? No. So let's keep going. So we set the scene. We realized that what is SDN? Let's go over the definition again. SDN is an architecture that is dynamic, manageable, cost-effective, and adaptable, making it ideal for high bandwidth dynamic natures of today's application. Note this definition doesn't talk about control plane and forwarding plane, because that's where it started, but that's not where the SDN ended up. We all thought that OpenFlow and the OpenFlow architecture would be the SDN, but in fact, it became just one of the southbound interface protocol that exists. It doesn't define the whole philosophy of what an SDN controlled network looks like. So it's basically it ended up just being an architecture, a philosophy that you follow in running your network. So the next line, the architecture still decouples. There is a decoupling between the control plane and forwarding plane, but that doesn't mean that your device doesn't have a control plane. You are just offloading some of the capabilities, some of the functions which you were executing locally on the device, but instead now relying in those functions running on the central controller. Why run it on the central controller? Because of all these advantages which I was earlier talking about. A controller might have a better view of what's happening in the network. It can do better correlations between network events. It can react better because it has a better view of what's happening in the network rather than a view of a device which only has information adjacent to it. The link has broken here, or I've just learned an event that my node understand. But an SDN controller with the global view might be able to do it better. Then basically the NBI, again, we talked about it. It's a communication channel between what's on top of the controller. So these could be OSS, BSS devices. These could be applications, anything that can talk to your controller via an interface. That's an NBI, and SBI is the interface communication channel between your controller and network device. And those devices can be both physical and can be a virtual as well. So even within the data center world, within in virtual networking, you will see SDN being applied much more better. And you will realize that it makes a lot more sense. If you are able to spawn VMs programmatically, you should be able to network them programmatically. And again, that's where SDN comes into the play. You spawn the VM, you spawn the workload, you can connect the networking by pushing networking rules via the SDN itself. So it works not just on physical devices, but on virtual world as well. So next set of thoughts are all going to be on SBI. So before we jump into SBI, I wanted to just cover what are the protocol choices that we have on the northbound interface space. So northbound conceptually is an interface between your SDN controller and higher system. As I said, that higher system could be anything. What are the common technology? RESTful APIs. These APIs are very common in the cloud world and all the other application world when they communicate with each other. And we use the same API mechanism also between the SDN controller and the device itself. Another very common protocol is RESTconf. In ITF, there was actually a netconf protocol which got developed first, very much focusing on configuring network devices. RESTconf was an extension of netconf and redesigning of netconf based on HTTP. So instead of relying on SSH and TLS, RESTconf was based on HTTP. Since it was based on HTTP, it could simply use all the HTTP methods like get, config, all those get, put, post very, very easily. Your applications already know how to talk HTTP. They can easily use RESTconf over it to make it work. And then there were YANG models. Now, I will cover this again, a little bit more detail in my future slides as well. But the YANG models are again generic. They could be at the device level where you say, how do I configure a particular device? A YANG model for that. You can also have YANG model at the service level, where at high level, I tell how I want, for instance, a VPN service to be established in my network. I'm not talking about one VRF, go and configure this, but at a high level, I have these endpoints. These endpoints needs to be connected in a VPN service, and these are my traffic engineering requirements when you interconnect them. Is it a full mesh? Is it a star topology? Again, at a very high level, describing the service that I want. Those kind of YANG models are very common. They are used with RESTconf in the northbound interface space. So before I go ahead, another quick check. Any questions on SDN, on NBI? And apart from that, we'll move to SBI next. I think we are all good. Thank you. So what is the information that we carry in the SBI? I'm just talking again in the abstract terms. When a network device is communicating to an SDN controller, what kind of typical network information that we will have? So you see here, topology is the most simple one. Of course, the device needs to tell its own network topology, the topology that like I'm this node, this is my information, I have these links, and these are the peering points that I have that I connect with, things like that. This is my network topology. The network resources, resources in terms of physical limits, that this is the maximum bandwidth that I have on this interface, as well as things which are dynamic in nature. That at right now, what is my bandwidth utilization? Right now, what is the delay that I'm seeing on a particular link? these kind of network resources, the current status of those resources, as I mentioned, for both topology and services. And the newest thing that is happening is telemetry. If you want to automate your network, if you want to be reactive, you need network automation. And for network automation to function, you need the real-time status of what's happening on the device. And if you think of the old world, how we used to do this? We used to do this with SNMP polling or with our MIPS, and where you go to the device and keep asking, oh, do you have the latest information for me? That kind of model do not scale, does not work. We need real-time telemetry push of data from the devices themselves to a common place. And this kind of thing you saw in every place, even in your web browsing thinking. Nobody likes to click refresh. We would like our websites to be get updated via the server pushing dynamically the latest data rather than me updating physically on a refresh model. Network telemetry does exactly that. I want the latest information from my devices pushed in a push model rather than on a pull model. And that's where SDN and the SBI interfaces play a very important role. Now, let's go in the other direction. What is the typical information that we are going to flow from the controller to the device? Though I earlier mentioned configuration, we should not limit at configuration, but configuration is the starting point of how anybody communicates with a device. So sometimes we want to do this configuration on a fast level and change my configurations as well. So that device configuration doesn't go away. It's still there. Similarly, I am binding services, I'm binding maintainability, enable OEM on a particular interface, collect more data, no need to collect more data. These kind of OEM information also needs to be dynamic based on what's happening in my network. And also, finally, is expanding my interface to go beyond configurations, things which were typically internal to a device, which they never used to expose. But in SDN world, they can be exposed, where you can go and programmatically change instructions on a particular device. I'll go and give some examples, and that will open up this as well. So at a high level, this is the information in both direction that you will see in any SBI interface. One thing which I also want to cover is you're never going to have just one controller in your system. We can all agree that that's never going to scale. There are going to be multiple controllers that you need. And if you need multiple controllers, of course, there needs to be a protocol that needs to run between those controllers. And it's very important for us to, when we are comparing SBI, to also think, can that same interface that I'm using to talk to controller to device can also be run between controller to controller? And some protocols are very good at it, and some protocols are not that good at it. And that's why it becomes a factor when we are comparing them as well. And at the same time, the way controllers are talking to each other are not same. There are cases like there are multiple SDN controllers in the same instance. Why we have that? For load balancing purpose. We know for load balancing for resiliency purpose, we want to make sure there are multiple controllers that can take over if one of them goes down, or just so that I can load balance things. I know that I have thousands of devices. Maybe one controller manages 500 of them, another controller manages 500 of them, and they load balance between each other. So those kind of systems are very common. What happens right now in lots of controller space, some of them rely on their proprietary database syncing technology, which is very common in any application space. Think of this SDN controller as just one app. And if there are multiple instances of app, maybe I can use a proprietary database sync technology between it and make it work. And some people actually do that. But there is also a case of maybe having SDN controllers from different vendors, and you want to realize not on a proprietary system, but an interface, and that is standardized so that it can run between any instance, and that's where it comes in. The another thing is peer-to-peer. What that means is you have two networks. I have a diagram, maybe that diagram can better explain this. So the first one is multiple instances of SDN controller for the same network. The second one is the peer model, where you have two different networks, each has an SDN controller, and these two SDN controllers are pairing with each other and sharing information on need basis. Of course, this is done only in case when there is some business relationship, some established trust, then only you would be exchanging this kind of information. The third one is how to scale. And for scaling, you would sometimes need a hierarchy. So idea of having a domain level controller and then multi-domain or a parent controller, which can uh, further consolidate and coordinate across multiple controllers. Again, we don't want a new interface. Can the same SBI interface that I'm running can run here? So if you take example of BGP or PSAP, whether they satisfy these models becomes an important question. And that's my last point. Why does this matter? The requirements for SBI towards devices could be same as they are from controller to controller. So that's why this becomes an important point for consideration. Now I come to the meat of what we are talking today, which is the most popular SBIs out there. We have BGP, Border Gateway Protocol, we have YANG-based protocol, those are NetConf and RESTConf, which I mentioned. And in fact, there are other ones like Google RPC, GNMI. You might have heard these names in Google's presentation. They have some of them as well. They also rely on YANG models, and they can easily map between protobuf and YANG models. So lots of good technology there, but all sort of data modeling based interfaces. And finally, PSAP, which stands for Path Computation Element Protocol. It's basically goes much earlier than SDN. And this is where basically we realize that, oh, a lot of things that PCE does, which was there for a different system. It was there so that we could compute better RSVP TE paths. Instead of relying on CSPF running locally on your device, what if we have a controller that does better path computation? That's how it started, but it evolved into meeting a lot of requirements of SDN space, and that's where PSAP comes in. So these are the three most popular SBI. Let me just have a show of hands. How many people know BGP well in this term, like understands BGP? Very good. How many people know YANG? Okay, so I'll cover some more on YANG and PSAP. Not many. Okay, so that gives me where I should spend more time today. So we'll go quickly over BGP, spend more time on YANG and PSAP a little bit. I think, do you have a technical issue? Or are you getting the bounce? Yeah. Oh, okay. Thank you. Sorry. So let's talk about most popular SBIs. We'll start with BGP. BGP stands for Border Gateway Protocol. It basically enables us to connect our internet, each domain, each BGP speaker across each ASS, runs eBGP inside your AS to run iBGP and basically exchange all the routing information. One thing which is very important in this is actually BGP LS, which is an extension of BGP to carry link state information. Very much suitable for carrying topology information from our network devices to a controller. So I'll talk about that. There is an extension of BGP. There's a whole thing about what we think BGP is, but BGP actually can carry a lot more information. There is the whole VPN information that we carry on BGP. BGP link state is this, and there are future lot more work because BGP is one of those protocols that is ubiquitous, that is available everywhere. And the design of BGP with NLRIs, with the system allows you to extend BGP to carry a lot more information pretty easily. YANG, again, it's a data modeling mechanism. It can be carried over multiple protocols, NetConf, RESTConf, gRPC, and finally PSAP. So let's jump directly into BGP. Okay, why? There's a little bit of delay. Okay, anyways, I don't know why I'm seeing this. Let me share again. Maybe that will better. And that's weird. Should I just do my whole screen because it's showing incorrectly? I don't know why that's happening. Enter full screen. See, this weird bubble is coming. Maybe stop sharing and start again, I guess. If it's a sharing thing issue. Share, review, share, view, slideshow. This is gonna be a problem. Or maybe let me just share the screen. Stop share and share. Sorry about that. So while we talked about the three ones, you will see there's a whole list of uh, other SBI protocols out there. Some of them, of course, OpenFlow is very important. SNMP, people have been using SNMP as a southbound interface as well. Again, one thing that I wanted to highlight in this was XMPP, OBSDB, IGP, gRPC. In optical world, you have PL1, P4, which is a programmable interface to put program instructions on your device. P4 is also being there. So there's a lot of work with different protocols being out there. BGP, let's cover a little bit about it. Why BGP makes a lot of sense for an SBI protocol as well. First, almost every network out there has BGP. This implementation exists already out there. We know how to use it, how to configure, how to make it work. It has very good policy implicant with your BGP in routes and out routes. You can put a lot of good policy information, a lot of filtering information, again, which allows you to use BGP as a mechanism to exchange information between your device and a network. So let's go over them a little bit. So we talked about iBGP, we talked about eBGP. Let's focus on the MPBGP, and that's where the SDN part comes in. The multi-protocol extensions of BGP basically allowed BGP to carry a lot more information than just IPv4 routing. Though it started with that, but with this, you can carry IPv6, you can do multicast, you can do VPNs. Almost all flavors of VPNs from layer 2 to layer 3 to eVPN, they all rely on the same multi-protocol extension model. And similarly, when we are coming up with the new data in the SDN world, the same thing can be done via BGP. So BGP allows extensions in a pretty neat way that could be used. Then if you look at basic BGP, you have path information, the policy support, the NLRI encoding functions, which is network layer reachability information, which allows you to differentiate information in a very good way. You have concept like route reflector, that is, I can easily use BGP route reflector to not have BGP session with every device, but only having a session with the route reflector, which can give me all information about the network as well. So this is a good slides on how the route reflection function of a basic BGP works. And I can utilize them without doing any changes. They will simply work out of the box if I use BGP as my SBI. Similarly, if I look at BGP LS, this is a new address family, AFI and AFI-SAFI being described to carry IGP information. So whatever information that is actually internal to the network, encoding that over BGP is basically what BGP LS was, letting me transfer the traffic engineering information and link state information internal to a particular network into a controller. It uses BGP scaling, it uses all the policy that you can provide, as well as new NLRI types like, for it, networks is made up of nodes and links. So I have that information. I have information about all the attributes, as well as all the information related to segment routing. If folks were there in the earlier training today about all the segment routing and SRv6, all of these things can also be carried inside BGP LS. So BGP LS becomes a very interesting SBI choice out there. So you can use the root reflector function. You don't have to connect to every device. You just use the BGP LS to talk from an SDN controller to the root reflector, and root reflector will further collect all the other information via IGP itself. So pretty straightforward. Now, let me cover what are the BGP extensions that already happen for segment routing, and why they play a very important role in the SBI place as well. The idea of using BGP prefix sets, which is the as well as we do egress peer engineering, which allocates segment identifiers to BGP peers, very much the way that we are going to do our eBGP configurations. Similarly, you have SID configuration. So you can use those prefix sets and do egress peer engineering in segment routing itself. So before I go ahead, how many folks understand segment routing? Is everybody in the room familiar with segment routing? Oh, I was under the impression that people would be attending other trainings as well. So in my slides, I haven't gone too much into the details of segment routing, but I'll give you a very high level this thing so that this slides becomes easy to digest. How are people familiar with traffic engineering, RSVPT in general, things like that? Some are not. So let's start in a very simple way how we can explain. Given a particular network, what we usually do is we route based on destination. We simply look at our destination in our packet, and we have our routing table, our forwarding table, all based on destination, and that's the only thing that decides who your next stop is, and you forward. The source routing says that instead of me making decisions at each node and each node looking at the destination and deciding who my next stop is, what if I can carry the network path in the packet header itself? So what would that changes? It basically would mean that enough information is carried in a packet header itself beyond destination. Still have the destination. Your IP headers haven't changed. They still have source and destination. But I also carry a network path, a source routed path in my packet itself. That's basically segment routing. So, and how do I carry the source routed path? By having segment identifiers, something that identify a particular node, a particular link, or a particular prefix. What kind of data plane I'm going to use? Usually MPLS. Luckily, MPLS allows you to label stack. And what I can do is each type of segment identifier can easily become an MPLS label. And by stacking that MPLS label, I do segment routing, which is called SR-MPLS. In the IPv6 world, we also do something called as IPv6 has extension headers. And one of the new extension header got defined, which is called SRH, segment routing header, where you carry the whole path that you want your packet to take inside that extension header itself. That's basically segment routing in the nutshell. Now, what happens is if you want to do this, you still need the path information to be programmatically configured on your devices. And that's where BGP is coming into picture. So the prefix sets, you can do allocation of a set. You can identify the path that you want to take. That path information, which you see as segment routing policy information, that can be encoded in BGP itself. So that is what's happening on this slide. BGP-LS allows you to carry the SID information to the top, and the SR policy information is the path that I want a particular flow or a particular service to take. That gets pushed down via SR policy. Are there any clarifying questions that I can answer on this before we move ahead? We will be covering segment routing comparison in few slides. So this is an important thing for you guys to understand. So if there is any question that I can answer, please let me know. No? Okay. So again, just in a picture format, what you are seeing, there are 3 ASs. These are the SIDs that are configured, which identifies each of them. And basically what we do in a source routed path, by using the peer adjacency SID, you can actually identify the exact ASBR link that you want a particular packet to take. Now just compare this with basic BGP. What will happen in basic BGP? You just have a destination, and it is going to be the routing information within your node that decides what your next hop has to be. So whether we use ASBR1 or ASBR2, that decision is taken at each network node, not at the source of the node. With source routing, by controller putting the SID information in the packet itself, you can control which ASBR, which ASBR link, which egress I should go through. So that kind of control you get via segment routing. And this is an example of how an SR policy looks like. So what is there in the SR policy? You have endpoint, you have binding sets. I think the main thing is the path, the CEEB, which tells what is the path this SR policy take. And you can configure this SR policy at a particular node, and then the packet will simply follow that path along. So that's what's happening in the SR policy. Okay, what are the other interesting things in BGP? BGP does flow specification, flow spec. You can do, which was initially done for DDoS mitigation, but now it's being used for a lot more things. And the same concept can be used for programming SDN-like use cases as well. BGP has community support, AS federations, route filtering, and ability to tell various different types of tunnel, whether I want to use IPsec, L2TPv3, SR policy, a lot of things which can easily be used in SDN use cases as well. And another thing that is happening is support for coloring. What that means is adding a very specific meaning to a particular service by giving my intent via colors. So even SR policy has a color attribute. And even without SR policy, also BGP has been extended to add color as one of the attributes in my BGP routing. So it becomes quite useful for services here as well. So this is a simple mind map of various BGP extensions. You have all the features that I was talking about, MPBGP, flow specification, BGP-LS, segment routing, a good idea of where BGP has been heading. Now let's change track and try to talk about YANG for a minute. YANG initially was called yet another next generation, sort of making fun of itself in a way. It all started with at ITF at an IAB workshop, people thinking of what will be the set of requirements. We have seen SNMP running and MIB running for a very long time. We know what are the issues that we have with this. Now let's think, what is the next generation for my data modeling? What will be the next generation for my network management? What kind of protocol, what kind of things that we want? And that's where both YANG and NetConf started. And let's try to break this down. YANG is basically a data modeling language. A YANG model is basically a data structure which can be used with various different protocols. So there's like the same way how SNMP and MIPS are two different things, and SNMP is your protocol, MIB is your modeling. The same thing is true here. YANG is your model, and NetConf, RESTConf, gRPCs, those things are just your protocol. And then what we could do is we now need to do various operations. What are the operations? Go and configure something, get me the status, let me run some execute at RPC, which is a remote procedure call, and get notifications from my system. So those kind of thing I still want to do. And if we compare it to SNMP MIB model, YANG is more hierarchical. You remember MIB models, if people have seen, they are just one flat long structure. They don't really use a lot of groupings, a lot of hierarchy, a lot of reuse of things. Those were the things that people identified early on, making sure the YANG achieves that. And in fact, there was one more thing with respect to an ITF. There was a working group called Interface to Routing System, which also looked at not just doing configurations, but what if we put ephemeral state into my network using the same set of interfaces? Now, what ephemeral would be? We all understand configurations. Once you config something, it lives on, and once the device goes down, device comes up again, the configuration will still exist. You will have systems in which you would be able to configure the device quickly. Ephemeral state is temporary state that is just pushed and it will get lost when that connection goes away. And with ephemeral state, we could do a lot more programmatic things rather than always thinking of them in configurations. So that's another thing that happened at ITF, which used Yang modeling and Yang techniques differently. Initially, there was the whole thing that we might need a new protocol in this place. But I think we quickly realized that no, Yang achieves these purpose quite well. This is just an example of how a Yang model looks like. Very high level, you have a module name, some organization, revision, containers, leaf list, and this is how the various structures that you can do with Yang. And try to remember how MIB looked, where you had one flat structure. Here, having container inside a container and allows us to do various groupings, various things, a little bit more better in that way. Now, netconf is like, as I was mentioning, is more like an SNMP, while Yang is more like model and MIBs. Netconf is a protocol to install, manipulate, and delete configuration. So it was very much focused on the configuration part, and in fact, very much focusing on the network devices themselves rather than the controllers. One more thing that was there was it was a little bit more tightly coupled to SSH, though now netconf on TLS is also there now. But initially, SSH, very much XML only, and things like that. But if you look at what are the different layers there in netconf, you will see at bottom a secure transport, SSH, TLS, things like that. And message layer, we have everything is an RPC. Operations are basically edit config, gets config, things like that. And finally, you have your content, the actual data which we carry in XML. So these are the 4 layers: the content, operations, message, and the secure transport that makes up your netconf. And what you see on the left-hand side is basically a message flow that's going to happen. You first need to establish an SSH connection, and then basically it's the RPC request. Everything is an RPC request at the end of the day between the netconf client and the netconf server. This is a high-level netconf message that on top, everything starts with an XML. Then you see the messaging there, which I mentioned was an RPC. Next, you see the operations, which is edit config in this case. You are telling that I'm going to edit my running data store, and this is the operation and the content that is happening. Now, the content is very tightly coupled to the Yang model itself. So the Yang modeling is basically telling that is site is the top leaf, and inside this, I have various other leaf parameters like instance ID, description, VPN name. So this structure is coming from the Yang model, and the actual message is in form of XML that is being communicated between your netconf client and a netconf server. Another important concept to understand in this thing is the idea of data store. So what you are configuring, that gets stored in a config data store. Once it is actually executed, then it goes into the running data store. And then you may also have a candidate data store. That is, if there are multiple people trying to configure the same device, you still need to maintain candidate before it gets executed. So that all concepts were taken care. These were the problems with SNMP that people had faced at the start of the protocol itself. They wanted to take care of this in a way. And similarly, startup, the set of things that are going to survive even when the device reboots. Whereas if you look at now RESTconf, very much like netconf, only thing that got changed was it's going to be an HTTP-based protocol. And you could use all the HTTP mechanisms, things there. It also allowed use of JSON, though you can carry XML as well, but RESTconf plus JSON is the most common permutation that is already that gets used a lot. And here also, if you want to break it down, what it looks like, you have your content, which as I mentioned, is usually JSON in this case. Operations, which are exactly like your HTTP. All the create, read, update, delete, everything that we do in HTTP looks exactly the same. And since it's running on HTTP, you can use the TLS functions to provide security, and which RESTconf does mandate. So basically, these are all the HTTP messages that you are already familiar with, and the protocol simply runs on top of it, like get, patch, put, post, and delete. Now, what were the initial problems with SNMP and MIB and why we went in this direction? There was the whole issue of we cannot have a support for transaction mechanism. There is low configuration efficiency, no network level configurations. What that means is every MIB was very tightly coupled to a device that's used for device configuration. If I want to configure something at the network level, that was not supported. It was based on UDP. It was, so of course it had, like, the whole security thing and other things were coming into play. Poor performance. MIPS are not easy to extend. They are flat structured and difficult to secure SNMP. Those were the key points at that time. And now when people thought that, oh, we are thinking of a new modeling language, what are the properties that we want to make sure that they have? We want it to be easy for humans readable, easy to learn representation. That should not require you a huge tutorial for you to be able to write Yang model. You can refer other Yang model and able to do that. Make it hierarchical, make it easy to reuse, and which was one of the big problems with MIB definitions as well. The ability for me to refer to deviate, like even if I want to reuse something but make small changes, that should be easy to allow. And that's where the extensibility and the augmentation function comes in. RPCs, formal constraints for configuration validation, better way for me to configure and control things, data modularity and versioning rules. So those are the some high level things at Yang. And I think the key part, which I already mentioned a few times, was the network telemetry. So here also the Yang and the Yang push techniques and netconf, various extensions have been made over the original netconf to meet the requirement of network telemetry. So what is this requirement? The main requirement is I want to learn as my network, any information gets changed as soon as possible. Instead of SNMP pull model where I have to always query, I want to know, I must have a session with you all the time, and moment something change, you can let me know immediately. And I can also have programmatically tell what data I'm interested in, so that you just don't bombard with me all the information, but I should be clearly be able to tell this particular parameters inside my Yang model. When that changes, you let me know. Otherwise, no need. I'll query when I need to. So things like that was very important. We call it streaming network telemetry because we want it to be continuously being streamed. As soon as there is a change, we want to learn immediately. And various protocol enhancements that happened to support this. NetConf had an event notification mechanism, but that was not really sufficient to meet the network telemetry requirement, because those were things like session down, which is like, oh yeah, session down, let me get a notification. Not really suitable for other things. We cannot have actual configured notifications like that. We want them to do this in a programmatic way. So that support got added. Yang push, the way of us to use even UDP-based notification, that is only for notification, send them on UDP, that's also supported, and more adaptive and distributed notifications. So this is how the telemetry looks like. On the left-hand side, you are doing query every 5 minutes. And in the other ones, you keep receiving latest information as anything gets changed on your network immediately. And basically, just getting latest data is not enough. You need to actually use that data. And that's basically gets called into our what we call as closed loop systems, in which you collect the network data, you have an analyzer that analyze that what actions that I need to take based on the latest data that I'm collecting. And then controllers, the SDN controller comes into the play and can push network changes to meet the requirement of telemetry. So until we are doing this whole cycle, then only you see the advantage of network telemetry and SDN. Just doing one element is not enough. I think I covered this part. So this is the mind map for NetConf and Yang, various things that you see on the Yang on the left-hand side and other things on the right. So before I move ahead, any questions that I can answer on NetConf, RESTConf, Yang, network telemetry, any doubts? Is the pace okay? Am I going too fast? Any feedback? All good. Okay, let's talk about PC. This is where I come in. I chair a working group called Path Computation Element Working Group at PCE. So this is something that I've been deeply involved in a very long time. So what does it stand for? It's basically a mechanism to support path computation for traffic engineering purposes to control what traffic flows on what flows. Why would I do that? I would want to do better resource optimization. I want to do more reliable services. That is, when something goes wrong, there's an immediate path available for me to switch. I do better planning for my network, better management, a lot of advanced services. So these things are driving for me to do centralized path computation where there is a global view of my network and I can take multiple things into account while making decisions. So let's take and try to map this into where, for instance, let's look at Google Maps. When I have to do any path setup, I put my source, my destination. Sometimes I put some constraints. The constraints could be, oh, don't go through any tolls, avoid ferries, I'm scared of water, and give me my final result in parameters that I understand. Don't give me in miles where I have to convert. I'm a kilometer person, give me in kilometer, things like that. And then somebody does path computation, shows you the path, gives you various links and nodes that you need to pass through. PSEP works in a very similar way. You have endpoints, you have constraints, and a central entity that can compute paths on behalf of you by looking at various information that is collected from the network. Again, BGPLS can help there. Via BGPLS, I have learned the topology information. I have the path. I have my traffic engineering database. I may also have information that I've learned from outside my system. Combine all of them and do path computation. Think in the same way as a Google Maps system, which is collecting a lot of traffic information from everywhere, but at the central location deciding. If we compare this to a non-SDN controller, non-PC system, basically me making decision at every junction. I moved from one place to another and then decided, oh, which of these paths I should take without checking the global view. I'm making decision locally. Among the three destination, which road is empty right now? Okay, let me just go there. That's the way. So what is PC? PC is the controller, is the central element that does path computation, and PSEP is the protocol that is used between a client, which we call PCC, and PCE, and in fact, in between PCs as well to communicate with each other. So, and PSEP relies on TCP, and in fact, it also has a TLS support. So it is pretty secure, and you can use TLS 1.2, 1.3 with PSEP as well. So in a pictorial way, basically, a node, when it needs to find a path, it go and talks to PCE. These are my source, this is my destination, these are my constraints. Tell me what path I should use. It gets the path, it signals the path. So initially when PSEP work started, and PSEP work is much before the SDN and all was there, main requirement was from the RSVPT tunnels. As we know, RSVPT tunnels use a control plane to go an established path in MPLS for traffic engineering. You need to know the path. Earlier, that path computation was local to the device, where a local CSPF algorithm was implemented. You used to compute based on that. PSEP allowed me to offload that to a specialized controller. And there was the protocol in between, very tightly coupled to RSVPT, because that's where our beginning was. But later, paths are needed for a lot more technology, segment routing being one of them. So even SR-MPLS, SR-V6 paths can be computed. This technology is very much useful in the optical world as well, where both for WSON, for GMPLS, paths are needed everywhere. And the properties of path can be implemented in this way. So PSEP is very popular in the optical world as well, not just in the packet. So if you look at a very high level, this is how the basic protocol exists. There is a request mechanism, and based on that request, you get a response. And of course, to make sure that you have a finite state machine, you have open, keep alive, notification, error, the general FSM that you always see. Initial PSEP was very simple. It's just request and response. But later, we thought that no, it needs to be extended a little bit. So what was the extension? Was to make it from stateless to stateful. That means the PC remembers all the paths that are also existing in your network so that it takes that into consideration when it's doing the path computation. So in a stateless world, basically, I only have topology. And at that time, somebody asked me, give me the best path between these two, A and B. These are my constraints. I compute the path, I reply the path, and I forget. That's the stateless world. Stateful, I remember every path that is already there in my network, so that once I do a new path computation, I can take the existing paths into consideration, making sure my whole network is optimized, not just give the best path at that moment of time. And then the next step was also to allow PC to control the path. So what that means is I have delegating the control of this particular path to a controller, so that moment anything changes, the controller can recompute immediately and give me a better path instantly. And now let's compare this to a stateless world. In stateless world, what will happen is I computed the path until the path is broken. The head-end node will not come to know something is changed. Only when things break, then the head-end node has some code which says, oh, let me recompute the path. And then it asks PC again. But in the other world, network, something changed. The controller can find out on its own that I need to recompute the path, give me the new path, and it's established. And the final update that happened was the ability to have PC initiated paths. That means you don't even have to configure the paths. The paths will be ephemeral in nature. That is, the controller can create paths on its own using a PSEP mechanism. That's where PC initiated comes in. And the final thing that we did was making sure that the PSEP can actually run very much like an open flow protocol. That is an ability for us to transfer central controller instructions, we call them CCI, via PSEP itself, where I can go and now talk to individual nodes along the path, not just to the source node, and ask them to make changes, very much like how an open flow system would. So that support also is there in the PSEP. So if you look at in a diagram way, instead of just giving the path to the head end, path to the head end is still needed. But I can also go and program the forwarding path on those nodes as well. And that's where PCC is there. So it's very much a lot of SDN functions are there in PC already. We talked about segment routing. Again, PC is in fact one of the main brains behind the segment routing space. Until unless you have the right path, the ability to put the path in segment routing is just the mechanism. But PC is the place where you actually can compute that path, make sure that it's resilient, you can re-optimize it, you can do all those things. So that's where PCs come in. And of course, then PSEP becomes a very convenient protocol to use between controller and devices as well. So at a very high level, what's happening is we talked about BGPLS. That's how you're learning the topology. And then via PSEP protocol, you are computing the path. In this case, in a segment routing case, as I said, the path could look like a stack of labels, especially in SRMPLS. So these are the numbers that you see are the label stack in SRMPLS that is being pushed via the PSEP protocol. And just a mental map, I think this might not be visible very much, but PSEP has been continuously evolving. It started with basic request reply, a lot of new constraints, extensions for optical world, extensions for segment routing, extensions for multicast. There is even, so wherever you need path, wherever there is a central controller and you need a path, PC can come and plays a quite important role there. So now this is a good history. Now I'm at the second part of my presentation where we will quickly comparing these protocols. First thing is, how do we even compare these protocols? These are the few factors that I decided to look at. First is the messaging function. How are the messages formatted? What are the size of the messages? What is the unit of transaction in each of these messages? So does the protocol message structure, the FSM, and the way they encode these, does that work well in my SR use cases? That was the first question. Transport function. What is the underlying transport that this protocol is being used? How reliable it is, how secure it is, things like that, whether it is UDP-based, TCP-based, HTTP-based, things like that becomes important. How well do they fit where SDN is actually used? Use case fit. How easy is to deploy this particular protocol in your network? What are the unique features of the protocol that fits very well in an SDN controller environment? And generally, how easy it is to operate. So let's look at the first one, messaging function. As far as the model is concerned, BGP is basically you have any two peers, they connect over BGP. That's how BGP is. Some hierarchy comes in if you add root reflectors. And then, in fact, at ITF, especially in the segment routing space, BGP as a central controller is also pretty clear that we want to run BGP at the SDN controller, use BGP LS, BGP SR policy mechanisms for it to do. So this model fits pretty well. If we now compare it to Yang-based, the idea was the protocol is all about an NMS client talking to a device which they call as a netconf server. So device is called a server and the NMS is called a client. So it's sometimes very difficult for us in the non-Yang space to always have that switch. But that's what it is. But at the end, NMS is like a controller. So the protocol can fit well even in an SDN case as well. And now if you look at PCE, same. Clients, server, that's how the protocol was all about. We have PCCC. You have, in fact, much better inter-domain handling because that was one of the key use cases of PC from a very, very start. The ability for me to talk to multiple network domains, compute end-to-end path, do hierarchy of controllers, those things are pretty well suited. So that's the model. I think all of them are doing pretty well at the model layer. Now let's talk about messages. If we talk about messages, BGP has tiny bit advantage. They already have this multi-protocol extension approach. They already do it for a lot of different things. Adding a new NLRI, a new AFI-SAFI, pretty straightforward. TL, sub-TLVs, pretty straightforward. Since it's binary encoded, the messages are much smaller as well, which when we compare with JSON and XML, you will see the message size is sometimes a problem for netconf and restconf cases as well, especially in telemetry cases or other cases, you are pushing a lot of information. If you want a lot of information where a CPU usage was uint 18, but in a netconf, it would look like a whole Yang model with lots of characters, a lot of these things, your message size adds up when you are doing things. And finally, PSEP, again, messages, we don't have address family there. So what happens is your message gets a little bit overloaded. The same thing is being used for multiple use cases. So it gets a little bit clunky, whereas in BGP, things are much more nicer by having AFI-SAFI. So transport function. First one, BGP, runs on TCP. We know that. Where BGP suffer a little bit is our security is not that clear. Of course, we have support for TCP AO. There are things that happen. CIDR is working on various different things. But the BGP security model is based on actually eBGP. It's based on people that you are not really trusting that much, right? It's between one AS to another AS. That kind of a trust relationship. Here, the trust relationship is within my network between controller and device. But at the same time, the information that I'm carrying will be very, very critical. It's going to have huge impact if things goes wrong. So I need to make sure I'm authenticated, I'm secured. I need TLS like something, but it actually doesn't exist right now. So BGP security becomes a bit of an issue if you are considering that. Now let's take about Yang. Yang supports all secure things. You have SSL, you have TLS. You can rely on HTTP security, especially in case of RESTconf, pretty good. You have things like netconf access control model. That is, you can specify particular leaf that only a few people can modify, which is a huge advantage. You can identify things in the data model by saying this can be modified, this cannot be modified, or only people with this access are able to touch this, which is very important in this world. And finally, in TCP, it supports TCP AO, TLS is also there. So security and transport is pretty good in this case as well. Use case fit. Let's compare those things. In case of BGP, BGP-LS, I think that's the best. That's the industry standard. Everybody implements it, everybody's using. So BGP definitely wins with respect to topology collection. Of course, Yang is also there. You could use it, but it doesn't fit well because of the message size and this thing. You don't really want to get huge network topology information collected in one way via Yang. It's possible, not the greatest fit. Uh, and now let me just cover via BGP first. That would be easier. So we talked about topology, we talked about segment routing. BGP is quite good fit in IP networks, so they can use all the MPLS IP, but optical, oh, not so much, right? So that's where you would see some difference. That fit, uh, it doesn't have a mechanism to do request reply. Like BGP messages are not meant to do that, but some of the SDN requirements are going to look like request and reply. If I want some information in a request reply mechanism, BGP is not your friend. And there are hacky ways and people have done it. So you send, for instance, a totally different message with a totally different address family from a controller to a device. Your requirement information is coming in BGP LS in a totally different AFI-SAFI. It's possible, but not the best. Doesn't have a good way to do central controller type things because you don't want to run BGP on your internal devices anyway. Who wants to do that? That's not going to scale. So anytime you think that I need to talk to my internal devices, BGP is not a good fit. Telemetry, again, you don't want to overload BGP with telemetry information, sounds weird. Configuration, automation, optical network, we do realize that some places not a good fit. Yang, very good fit for telemetry. That's what they do best. No other protocol can do network telemetry in a good way. Inventory, again, Yang does very well. Configurations, that's the whole protocol's job. It's written for a network configuration, they do it quite well. Automations. Okay fit for path computation. Why? Because they have RPCs. RPCs can be used as a request reply. So that they kind of meet the requirement. That fit for what I was talking about topology earlier. Big database like topology, getting it via this interface, not the best fit. PSEP, everything related to traffic engineering, path computation request, optical networks, interdomain networks, central controllers. PSEP has been able to do that quite well. They are pretty good fit. Bad, telemetry, configuration, automation. So you can compare, like, BGP and PSEP are very control plane protocol. So of course they lack those properties. Yang-based protocols are management-based protocols. So of course they do very well with configuration, automation, and telemetry. Ease of deploying. So if you look at BGP and IP networks, at least on your edge of your network, everyone has BGP. So it's going to be already there. The BGP code is already there on your device. You can just enable. BGP LS in controller is pretty standard. This is going to be pretty easy to deploy. You will have a harder time deploying in an optical network. Though there are implementations out there, especially for things like BGP LS, where people say that, oh, I don't have to implement the whole BGP stack, but what if I can just get the BGP LS address family support? Forget about the IP network. I don't even do think there are no prefix. Just use it to carry BGP LS. Yeah, technically possible, but there's nobody who's doing that because people are uncomfortable with BGP in that world. So they want to use protocols that people know, which is very reality. That's what happens. Use of BGP in data center, actually, that's very popular. You would see that Facebook and other people did this very, very early on. They tried to use BGP not for interdomain routing, but within their data center routing in their leaf spine switches quite well. So it is present and it can be used. Does it makes it practical to use even in a data center environment? Some other cases, access network, SD-WAN, I think yes, BGP can be easy to deploy. Now let's talk about Yang. RESTconf and NetConf are features that are there in every router, this thing, pretty straightforward. Optical network actually saw a pretty good adoption. They are moving towards supporting these things protocol. Initially, there was a lot of resistance, but I think in optical networks, you are starting to see. And their use cases were very much SDN driven, not to do actual configuration on devices, but because of the SDN sort of use cases, they realized that having a Yang model and even all of our GMPLS, WSON, everything that we do, layer one topologies, having them as a Yang model has its advantage. A lot of work is being going on in CCAMP working group there. Data center, useful, but people are not that, you have large scale configuration and automation needs, makes it quite well for data center. They have the need, but okay kind of support. In PCEP, it shines in optical world because it's already deployed there. In IP network for segment routing, SRMPLS, it works pretty well. Data center, not so much. You will not see PCEP in that field there. Access network, yes, it can play a role, not so much in SD-WAN cases. So this was a quick view of ease of deploying. Any questions so far? We have 3 more parameters over which we will be discussing. But before I go ahead, let's just pause for a second. Okay. Unique features. So what are the unique features that BGP has? Address family, support for multiple protocols. What that means is that you can carry multiple things. I was mentioning about BGP LS, for instance. So very distinct things can be easily carried inside BGP. You have support of NLRI. So the whole encoding mechanism that the protocol has, that adding new things, it makes it pretty straightforward. And everything at the end looks like a BGP update message. Don't have to worry about new message types, new this. Just add a new NLRI and it just works. So all you need is a new NLRI support across your BGP peers, and you can add more information straightforwardly. So what are your drawbacks? Not straightforward to direct a message to a single device. This is the biggest problem that you will see with BGP. BGP, as we say, is like, the update message goes everywhere. And even though I only want to let a particular device know a particular path, other people don't need it. The message goes to everyone, and everyone would have like BGP policy or other mechanism to figure out who is this message for, and other people would simply ignore it. How am I doing on time? 20 minutes. Perfect. So I think we are going pretty good. The next one that we have is YANG based, where the unique thing is vendor private augmentation and deviation being supported as a part of the protocol itself. Now just think of doing that with BGP and PSAP. It's going to be a disaster. Adding your own vendor stuff. Yeah, there are a few vendor specific TLVs that you can add, but it's very clunky. Like you have to recompute, recompile, redo a lot of things for that to work. YANG allows you to take a standard model, quickly write an augmented YANG model with deviations and vendor specific things right there, and easy to compile, easy to use. That makes it very good to do specific things for each vendor in an SDN system easily. Extensibility, again, adding new things into YANG, pretty straightforward. Telemetry, they do very well. Drawback, messages are huge, very verbose. Large data handling, the amount of data is going to be hard. Message size increases quite a bit. Again, what has happened is in our industry, we have not converged on the YANG model itself. So you would see in our industry, there are ITF models, there is open config model, and vendor specific models. And we are not yet converged. So that means that you might have to implement a lot of models in your system and a lot of conversions in your system. That makes things a little bit complicated. Whereas BGP and PSAP, you have a straight one. There's an ITF specified protocol, you have to just follow it. No changes there. So it just interoperates pretty straightforward. PSAP, since the protocol by default runs between controllers, so all the controller to controller handling is very well done in PSAP. PC also allows you to have a very clear hierarchy. Parent PC, child PC, this works very well. PC as a central controller, that means when I'm using my protocol to talk to internal nodes along the path, this is the only protocol that works quite well. Others, not so much, because PCC support is already standardized there. Anytime when we need to work between IP plus optical, a protocol that is well in use in both networks, IP and this, so you can use PSAP protocol for an IP controller to talk to an optical controller, do IP plus optical synergy, IP plus optical path computation, which is very, very unique, which PSAP supports. And again, they continue to be useful in an SDN world as well. Because just think, if you optimize the packet network but can't touch the optical and you want to program something, you need support for both of them. So that's where PC can play an important role. Operational complexity. So we know BGP is a much more complex protocol. It has a lot more configurations. You are also afraid that the same protocol is being used to do something others like the basic routing. And if I, because of my SDN use cases, I impact BGP basic function, that's going to be a disaster. It's going to be catastrophic effect. So that's a worry many people have of reusing BGP, operating BGP in the central controller way. Address family separation is one of the best thing that it can help with this operational complexity as well. Yes, that family exists separate, making sure it has less impact. Yeah, some benefit you can get. Yang, I think those are the most easy to operate. Any person, any network operator who's already using Yang model, RESTCON, should be able to use this for an SDN operation in a minute. No need to worry. Automations, very well supported. Support for many Yang models, correlation and translation between them. All of this is well supported and very useful in an SDN's world as well. PSAP would be the simplest protocol in this case, so it's pretty easy to operate. Its extensions are a little bit sometimes difficult. PSAP is extended for a lot of features, and then it becomes like, a little bit complicated in that sense. So final slide, at least on the comparison side, I have some more slides which deals with the use case fit, but at least for the summary of the various different protocols that we talked about today. Message functions, they have different approaches. Each has its advantage and disadvantage. Transport functions, almost similar properties, except for the security in BGP. Use case fit, again, BGP, PSAP both has good plus bad. Yang, actually mostly good. Ease of deploying. In case of IP networks and data center, BGP wins. In case of optical and IP, PSAP wins. Yang, pretty much everywhere is getting there. Unique features, I think all of them have some unique and drawbacks. Operations, BGP is complex, Yang is easiest, PSAP is somewhere in the middle. So that's where we are. It's like a mixed bag. There's no clear winner, there's no clear loser. It's sort of a mixed bag. So what happens in a mixed bag case? Most of the time, once an operator starts using a particular SBI, it ends up using that SBI everywhere. And it becomes a hard sell for them to change. That's where the reality happened, where an operator who was more comfortable with running BGP ended up using BGP for SR policy configuration. An operator which was using PSAP ended up using that. And in most cases, when they were not using either, many people chose Yang. And why they chose Yang? Because that is more future-proof. It allows you to do a lot more things easily. Whereas in other cases, the question was, what am I comfortable with? And people ended up using that. That's where, if I look at the history of what has happened, that is how I will summarize. So again, a quick break between comparisons, and I will now cover key use cases in my rest of my time. But any questions, anything that I can answer, any clarification? No, so let's go ahead. Topology. We said that in case of topology, BGP-LS is one of the easiest winner case. Basically, now I'm comparing all of this. First, we compared in an abstract way. Now I'm taking use cases and seeing for each of these use cases, which is the protocol that works the best. So what is the use case called network topology? A mechanism for me to learn the topology from a network so that I have a single view at the network. This could be routing information, this could be traffic engineering information, even the network telemetry part can come in this thing. I think we already talked the BGP-LS is one of the better ones here. These are some of the reasons. They support AFI-SAFI, so keep clear separations for the topology information. It's already well deployed. That's what BGP-LS has to offer. Yang has actually one advantage. The advantage that they have is, in Yang modeling terms, what you can do is you can have a base network, which is like any networks is just made up of nodes and links. Then what you can do is have a augmenting of that network of various different types. Now a network could support various different network types like optical network, layer 1 network, layer 2 network, layer 3 network, MPLS network, segment routing network, and you could have a very well laid out relationship between these networks. And you could, that is what Yang modeling supports. And that can give very good information over the other places. So BGP-LS just gives you, this is one topology view. Whereas Yang model can layer your topology very, very well. That's an advantage that Yang model provides. In fact, PCEP is also has a PCEP LS support, a mechanism for PCEP to transfer information, notes and links to the device. This is very popular in the PCCC kind of use cases. Since I'm using one protocol to go and configure the device, why don't I learn node and link information from there as well? But its deployment is pretty less, not yet deployed as much, but the support is there. Next, I have computed a path at an SDN controller. I need to now go and give that path to a particular head end so that it can go and establish that path. That path could be established via RSVPT, it could be SR policy, it could be open flow kind of system, PCCC kind of system, doesn't matter. Now let's compare how each of these protocols work from a controller to a device when I want to establish a path. BGP has a support only for SR path. You cannot use BGP for RSVPT, nobody thought of it. Whereas PCEP started doing that for RSVPT first and SR got added later. So PCEP is a unique way in which if you have in your network both existing, that you want to establish your MPLS RSVPT path as well as SR path, PCEP becomes a much better choice because via the same protocol, you can do both. You don't have to think of two different ways just because my tunneling is changing. Another thing that BGP does is BGP SAFI for candidate paths of SR policy that support exist, tunnel type, route targets. Those are the things that BGP can offer. Yang model for tunnel exists. Yang model for SR policy exists. Yang for compute only. What that means is that I don't actually want to set up the path, but I just want to know what path would you set up if I would have asked you. So that's called compute only. That is when useful for northbound point of view, like an app asking an SDN controller, imagine I wanted to set this thing, how would that path look in your network before I actually can commit for you to execute that. That's called compute only, which is also supported quite well in Yang world as well, which becomes very difficult to think of in BGP. Like when he's sending a message and saying, well, I'm sending you to do this, but don't actually commit to it. Oh, no, not really. Finally, traffic steering. What does traffic steering looks like? Again, BGP flow spec kind of stuff. Pretty neat because BGP already supported, everybody implements this. Initially, it was all for DDoS, but now BGP flow spec is being used for a lot more things, for L2 VPN, for various things that we could do with match criteria on address policies, on port numbers. So again, very much useful in SDN world as well. Yang, unfortunately, right now we don't have a standard Yang model, but I can foresee that in a few years people would do it. Right now there is of course ACL, and people would say that ACL can be just considered that, but could it scale? What are the issues? We can all realize. But I think there are better ways to do this in Yang, but it has not been done yet. PCEP has the same what we have in BGP flow spec. PCEP also support PCEP flow spec as well, so they are par to par when you think of steering. Segment routing. We talked about SRMPLS, SRv6, and SR policy. Let's look at how each of them are doing with respect to support for this use case. BGP supports SR policy, supports BGP LS. Yang, again, we have various different Yang models for each of them. PCEP also supports this well. In fact, in ITF world, segment routing is one of the key use cases for an SDN-like system, where a central controller makes better decision than if SR policies were configured or were computed only at the head end. We need a central controller there. Network telemetry and automation, again, BGP, no, we can't do that. Yang is the only good way to achieve this. They already support by default. They have been doing this for configurations and other things. So it makes sense in Yang world, not so much in control plane, which where the BGP and PCEP, so they both suffer there. Some future use cases. Again, I took one example. This is something that it's been still debated at ITF, whether we have a closer cooperation between applications and network. and ability to carry more informations in the packet header itself, along with SR path. What if I can also identify an application type, for instance? So again, thinking which protocol is better suited for extensions, for extensibility, and let's compare them. So BGP, for filtering, flow spec can be used, policy distribution could be used. Yeah, it works okay. Yes, you can extend. Yang, of course, because Yang data model are extensible. You can simply augment new information, it will suffice. PSEP also has a flow spec mechanism, so that will work. Getting no signal in, it's okay? Yeah. So PSEP flow spec will work, everything seems fine. Some emerging use cases, again, as a mental exercise, if you think of DetNet or Beer or various other things, yeah, it could work. So my final slide, which is looking at various SDN controllers out there, which are already there. You have owners, ODL, even some vendors. What protocols are supported, what are not. Right now, what is happening is most of the controllers are ending up supporting every SBI. And why is that? Because we don't have a consensus in our community of which SBI is better. And as I was mentioning earlier, people who are comfortable with BGP use BGP, people comfortable with PSEP use PSEP. What happens in the real world? As vendors, as SDN controllers, you end up implementing everything. So that's the thing that you will see on this slide as well. Now, what are the issues with that? Basically, what that issue is, your whole SDN systems become quite complicated and implement when you have to support all the SBIs. And most of the controllers have been very smart with this by putting SBI at the bottom layer as the last thing that they do when they communicate to a device. So everyone has an internal model, an internal data structure that can map to each of the protocols. Now, where it becomes difficult is when there is not a clear mapping, because there is one feature being supported here, one feature not being supported here, and this translations, it becomes a little bit messy, but that's where we are. So the whole debugging, multiple SDN controllers, this is the various operational issues that we see in the SDN world with multiple SBIs as well. And the final thing that I want to say is, many people think that controller is within my network, and since it's within my network, I can trust it. I don't really have to have a complex security mechanism between it, but that's not true. Just think about the kind of massive changes in your network that you could do over this interface. Earlier, you were not exposing this interface, but if you are exposing a particular interface on your device, even though you expect your SDN controller to be within your network and I can trust it, but no, if you open a port, you have to make sure that you secure a port. So make sure that the SBI that you choose is running in an authentication fashion, it's fully encrypted, you can trust it, because of the changes that you can make with SR path, with SR policy, with various different things. We can see that you can in fact have a lot more easier tools for your attacker to deviate and do traffic than what BGP could do. We talked about BGP hijack, we talked about various things and how much changes it can do in your network. But these SBIs are bigger security threats. So you need to make sure that you authenticate only my controller is sending this message, not a random guy in the world. So it's very, very important. We did cover this already, so I think I'll come back to my last conclusion so that I can end on time. Multiple SBI option is a reality, because there is not one SBI that fit all the use cases, that fit all the deployment preferences. There are no clear winner in the short term, but in a long term, Yang is one with the most advantages. And that's where we see an optical network, which was sort of not implementing BGP, not implementing Yang, but is quickly moving towards Yang. So I can see from a greenfield point of view, a person who needs to do this sees Yang as more future-proof as a mechanism to invest in. So that's where would be my last final thought, and would love to hear at least some of you say something. Otherwise, I've just talked through 90 minutes. So please, one question at least, or one comment from anyone. Quick feedback. What did you guys like? What you didn't like? Did you disagree with the conclusion?
I just wondering, can you clear about the BGP in data center? That's the BGP OSPF, right?
Yeah. So there is it's actually an RFC. So both Facebook and other people came and told how they use BGP as an internal routing system inside their data center, where each BGP server got a whole AS number itself. So they're using private AS numbers for each guy and using the distance vector algorithm instead of AS having a lot of devices. What if one server or one node gets an AS number on its own? So using that, they were able to do a lot of good routing. And what happens is, if you compare it with OSPF and ISIS, you have one SPF. Everyone has to have the same view of my network. That's what they are, general purpose routing systems. With BGP, because of the policy support, I could do a lot more interesting things about what kind of policy I want to put at my spine, at my aggregation layer, at the top. I could put right policies, right aggregation using BGP. That feature they exploited to use BGP inside the data center. And data center is a unique topology because it's sort of like it's a fixed. Everyone has one setup. And by knowing whether my peer is a spine node or a leaf node, I could do a lot more good, interesting things. And that's what being exploited there. In terms of SDN, what happens is if you're already running BGP, enabling BGP LS is such a straightforward thing. Oh yeah, let me just enable BGP LS so that my controller in the data center also uses the same protocol to learn the real-time thing. And that's what they did with, especially in the data center world.
So I'm not a Yang expert, but I work on FR routing, the open source stack. And I have to say, like, from what we have seen is Yang was quite a bit hype in the academic and also in IETF form, but there is about zero adoption on outside. Nobody seems to be willing to use it. And from most I have seen who tried to use it, gave up, because part is also Yang has quite a strict structure, which is defined by the IETF, the model. And frequently people implement it, they realize it for their platforms, it doesn't really work that way. So there is a lot of challenges, sometimes performance, sometimes they have to do property extension. So it's not that clear. So I would, if you think about Yang, think twice about it, I would suggest.
But it's valid to Yang is not ubiquitous because again, something to realize is who are the people who face the most network configuration challenges. So you will see very big ISPs, which are even evaluating and are doing things. So in ITF, for instance, most of the use cases are coming from Telefonicas, from Swisscom, from China Mobiles, people who are really big networks and who want to do this network automation, network telemetry like use cases. If you go to an enterprise network person, yeah, I don't need it. I'm very happy with my tools, and they would say that in fact it's too much complex. We really don't need it. So both things exist. But Yang has some advantages in the sense where Yang suffered was we not being able to converge. There are not one IETF model. As I was mentioning earlier, OpenFlow ended up with their own modeling structure saying that we know better. This is how you should model it. IETF did it in a different way. And in fact, every vendor who was supporting NetConf from ages had vendor models already because not all vendors have the same features. And some of them are not even standardized and you need to configure them. So a lot of vendors have their private models as well. That's where the complexity came in. And looking at that complexity is what freaks people out a little bit. That, oh, there are so many data models. I don't know what to fit. And it's not an easy guide to deploy it. But at least in the ITF and in the big ISPs, there is good movement there. While we did not achieve everything that we went out to achieve. But yeah, you can.
So I just want to add to that. I mean, I don't disagree, but there is two things between talking to the ISPs at the people on the research side, which go to IETF, and the operator sides, who most of them tell me like, I would never want to run it on my network. And it includes all the ones you mentioned.
Yes, which is very true. And that's why I prefer coming here as well, so that I can hear these inputs as well. I think we are taking other people's time. But thank you. Thanks for your questions. Thanks for your comments. I hope this was useful. Please come and give me private feedback as well if you didn't like it and didn't want to say that in public. Thank you.
Organization helping to provide security information. You can interrupt us at any time, right? Because this is a BOF session with it. We're going to walk through some of the basics and some of the reasons why we're doing the things we're doing. Okay, yes, got it. We are recording the session. There we go. So this is who well, that's Todd. I got Todd in there. So here's some statistics to think about. And the reason why I'm like doing a lot of work with Shadow Server. The cost to human society on cybercrime is getting to a point where people don't realize just how expensive it is on society. It's just, this is projections. So this is one projection where it kind of goes out and says by, 2028, $13 trillion, not billion dollars, $1 trillion, right, on the cost. This is a year old, the 2023 data hasn't come out, but when you look at like what are parts of society that's getting really hit by different types of cybercrime activities, notice right at the top, healthcare. Every day I'm seeing cases where someplace in the world, a hospital is shut down, they're not accepting patients because of a ransomware attack, right? So this is kind of like the world we're living in right now. When you look at, other numbers out there, statistics, coming up in 2024, this is like staggering how much cost factors that's impacting us, right? So put in another, 2024, $6 trillion, $500 billion each month, $1.15 a week, right? $1 billion, right? 16 a day. How much an hour? So every second society is losing $190,000, right, every second. This is kind of like the cost factor in there that we're seeing with it. So when you look at, like, for instance, projections, this 13 billion, what that means is how much we are spending. We are spending a tremendous amount of money trying to protect organizations. People kind of keep on saying, why are we spending all this money? Why are we getting all this certification? Why are we getting all these requirements? And how come we still get ransomware and DDoS and things like that? The attacks keep on happening, right? We're getting to a point, and this is probably a talk we can do